This conference will now be recorded.
Hello everyone. Last time we have finished salts of oxoacids of the group 2 elements. Now based on that is sulfate, carbonate, nitrate, all these salt of oxoacids of this group, that is group 2. Considering all this, we will discuss some problems. And once we finish this, next we will see anomalous behavior of the first element, which is beryllium, and what are the similarities between beryllium and the other element aluminium, because they are related to each other by diagonal relationship. Okay, and if we time permits, we can also discuss some important compounds of magnesium and calcium. Here we have this problem. It is saying that a metal which is A, on heating in nitrogen gas, it gives compound B. That means when we are heating it with nitrogen gas, we are getting B. Now B on treatment with water, we are getting a gas. Now this gas is colorless, that is this gas, when it is passing through copper sulfate, so copper sulfate plus this gas, if we are heating it, we are getting this dark blue violet color solution. So we have to find A and B, these two. That is, we have to find the metal and the compound of the metal that we are getting when the metal is reacting with nitrogen. If we look at the options, we have either magnesium or sodium as metal. Now, if we heat magnesium in presence of nitrogen, there is formation of Mg3N2, okay, nitrate, magnesium nitrate. But there is no such reaction between sodium and nitrogen directly. So, this option that is related to sodium, option 2 and 3, this cannot be correct. Now, here we have the metal Na and Na3N, that is sodium nitrate, but that direct reaction with nitrogen is not possible. And NaNO3, that is reaction with oxygen as well as nitrogen, because both the elements are present here. But here it is saying only heating with nitrogen gas. So these two cannot be correct, right? Now, among 1 and 3, it is fine that A is Mg. A is empty, that is fine. But when it is reacting with nitrogen, whether the compound is Mg3N2 or magnesium nitrate, it is actually Mg3N2. Okay, it is not the nitrate. So that is why correct option will be the first option. Now it is true, it is that is the first option is correct. But what will be the reactions, that we will see now. So magnesium 3, when it is reacting, it will form Mg3N2. That is magnesium nitride, where each nitrogen is carrying -3 charge. So that is by 2N, that means total negative charge -6. And to balance this -6, we need 3 Mg, because per Mg we have 2 positive. So total positive charge will be +6 if there is 3 Mg. So that is why Mg3N2 is the formula. Now when it is reacting with water, 6 water molecule, if you write the balanced equation, there is formation of hydroxide of the metal. But what is the gas? The gas is basically ammonia. Now this gas, in presence of copper sulfate, it forms a complex which is having color as it is mentioned in the question. So copper 2 plus, it will be surrounded by 4 ammonia molecules. So it is basically amine complex. Copper NH3 whole 4 and ammonia is neutral. So copper 2 plus, these 2 positive charge, that will be balanced by sulfate, but that is outside the coordination sphere. Because this is a complex, we write the structure in this way. So these are the reactions involved, and here the metal is Mg, this is A and this is B. So correct option is the first option. Okay. Next question, the alkaline earth metal nitrate. That means it is obviously alkaline earth metal question because we are discussing that. But we are talking about the nitrate salt of that alkaline earth metal. that does not crystallize with water molecule. That means, suppose I am writing any metal salt, and after that there is a dot sign and we write water molecules of crystallization in this way, NH2. So if it is strontium nitrate, then strontium nitrate NH2 or MgNO3 NH2. Different N may be any integer. Now it is asking that alkaline methyl nitrate we have to choose where no water molecules of crystallization is present. Now if you look at the options, obviously all are nitrate salt, but the elements strontium, magnesium, calcium, barium all are from group 2, that is alkaline earth metals. And if we arrange them, that is down the group, then first we have beryllium, but beryllium here we do not have. So I am writing starting with Mg, then Ca, then Sr, and then Ba. So we are moving down the group. So when we are moving down the group, this type of that is water molecules of crystallization, that is hydrate formation tendency, that is actually decreasing. So barium, which is at last position down the group, so this should be the correct answer. Okay. So here the explanation is the tendency to form hydrates decreases with increasing size and decreasing hydration enthalpy down the group. So as we are moving down the group, all are basically carrying +2 charge, calcium 2 plus, strontium 2 plus, barium 2 plus. The size is basically maximum in case of Ba2 plus. Down the group, size increases, and when size increases, the hydration enthalpy decreases, that is, it becomes less negative down the group. And when it becomes less negative, water molecules associated with the crystal molecules, this tendency will decrease. Okay, so that is the reason. Correct option will be the last one, that is barium nitrate. And this is the explanation. Down the group, because of increase in size, the hydrate formation tendency decreases. The correct decreasing order of stability of the following sulfates. Here we have 4 sulfates, 1, 2, 3 and 4. Now all are group 2 metals, magnesium, strontium, calcium and barium. Now if we arrange them down the group, first barium 2 plus, I am writing the cation part only. Then we have Mg2 plus, after that it is calcium 2 plus, and then it is strontium 2 plus. And it is asking the order of stability. Now, sorry. The explanation should be like this. Thermal stability order, during the discussion of sulfate, remember we have seen what is the order of thermal stability and also the order of solubility. Now when we talk about thermal stability, down the group, that is actually increases. Now thermal stability, though it is simply saying stability, but it actually means thermal stability. So down the group, what happens? As the size of this cation is increasing, right? The size of this cation is increasing. So the anion that is involved, the anion involved is SO4 2 negative, and this anion is common for all. Now polarization power decreases as size increases, because polarization power is related to charge density. Now charge density means charge divided by volume. Now charge is constant for all. All are having same charge 2 plus. So we have nothing to do with charge. But volume is maximum for strontium. That is down the group volume increases. That means charge density, because of increase in the volume, that is the denominator is increasing. So overall the ratio will decrease. And ratio will decrease for charge density. This value decreasing means polarizing power is also decreasing, and when polarizing power is decreasing, that means thermal stability, that will be very high. So minimum thermal stability, that will be for Be2 plus. So now if we arrange, strontium is having number 1 as mentioned in the question, then calcium is having number 3. For magnesium the number is 2, and for beryllium the number is 4. So it should be maximum is for 1, then 3, then 2 and 4. So that is why first option is the correct option. Fine. Though the explanation you can also check in the previous class when we have discussed the salts of oxoacids section. So sulfate is also a type of salt of oxoacid. It is the salt of H2SO4. Okay, so that part also you can check for explanation. Next problem we have, which of the following alkaline earth metal sulfates has hydration enthalpy higher than the lattice enthalpy? Now, we know that solubility basically depends on the combined effect of hydration enthalpy and lattice enthalpy. Because Deleuze solution, this value when negative, then only solubility in water is possible. Now, Deleuze solution, that is enthalpy of solution, is directly dependent on lattice enthalpy and hydration enthalpy. HYD, I am writing in the suffix. Now, the more negative is this value and less positive is this one, the chance is Deleuze solubility, that value will be highly negative and solubility will be very high. Now, when we have discussed sulfate, that is salt of oxoacid section in the last class, sulfate. So all these are basically sulfate. Now, the solubility of sulfate down the group, it is actually decreasing. So that is why BaSO4, which is the last element sulfate salt, that is actually highly insoluble. Now, if we arrange these four metals as it is mentioned here, so we have Be in option B, then we have, that is down the group, if we move, first is Be, then calcium, then strontium, and then at last it is barium. So these four metals are present here. You can also write the charge. All are having same charge. Now down the group, solubility basically increases. And the reason is when down the group solubility increases, that means Deleuze solution will become, down the group solubility decreases. Down the group solubility decreases. Now solubility decreases means Deleuze solution value will become less negative as we are moving down the group. So it will be maximum negative for Be2 plus. Now in the question, it is not directly asking the solubility order, because if it is asking, so it will be very flat question and we can easily answer that. But it is simply asking in which case, that is in which alkaline earth metal, the hydration enthalpy value is higher. That means hydration enthalpy is more negative than lattice enthalpy. Now it is another way of saying that when hydration enthalpy is high, this Deleuze solution will become negative, because Deleuze hydration is higher than L. Now when I am saying higher, don't consider the negative sign, it is only the numerical value of Deleuze hydration. And if you consider negative, that means it is more negative. So when Deleuze hydration is greater than L, then only solubility possible. Okay. Now solubility possible means maximum solubility is Be2 plus. So the chance is only in case of Be2 plus, this Deleuze hydration enthalpy, that will be higher than the lattice enthalpy. It may be also true, I am not saying that it is only true for Be2 plus, but as it is single choice answer, you have to choose just only one. And solubility decreases down the group. So maximum solubility will be for the first element sulfate, which is BeSO4. Now, if it is as maximum solubility, that means Deleuze hydration value, that is hydration enthalpy value, it must be greater than lattice enthalpy. Okay, so that is why considering all this, we have to choose the option BeSO4. Fine. Next problem. Now this is very interesting. See, it is saying that BeOH whole 2, beryllium hydroxide, reacting with another hydroxide. Now both are from group 2, that is BeSR, both are from group 2. But one hydroxide is reacting with another hydroxide. It is interesting. To yield ionic salt, and they are producing a salt. Now, based on this statement, you have to choose the incorrect option. That is, there are total 4 statements given in options 1, 2, 3, 4. You have to choose the wrong one. And these statements are related to the statement which is mentioned in the problem, that BeOH whole 2 reacts with SROH whole 2. Now, what kind of reaction we can expect between these two molecules? If you understand that, then only you can answer it. Okay, so you have to understand the reaction. Now, when there is a reaction between two molecules and it is saying that it is producing some ionic salt, so you can think about that it will be acid-base type of reaction, because in acid-base type of reaction there is formation of ionic salt. Now, how it will be acid-base? It is hydroxide. So, if you are thinking that it will be base, let me tell you, when we have discussed the hydroxides of group 2 elements, then we have seen down the group electropositive character increases. And when electropositive character increases for the metal, in general I am writing MOH whole 2. Now this M may be Be, Sr, calcium, magnesium, whatever. But down the group electropositive character increases means the basic character will also increase. So maximum basic will be when you have reached maximum downward. So if I am writing all the elements one by one, Be, then Mg, then Ca, then Sr, and then we have Ba. Now here we have only two elements. In the problem it is mentioned, there is mention of two. Now among these two, as Sr is much below than Be, so obviously you can expect basic character for it. And Be, I will not say that it is acidic, because it is after all having some metallic character. So its hydroxide cannot be purely acidic, because acidic hydroxide, oxide or hydroxide, that you get only from non-metal element. But these are not non-metals. Only that its metallic character compared to Sr or Ba is less, but that doesn't mean it is non-metallic. It is still having metallic nature. So its hydroxide is basically amphoteric in nature. Amphoteric means which can react with both acid or base. So if it is amphoteric and if Sr, its corresponding hydroxide is basic, okay, then you can think about that compared to strontium hydroxide, beryllium hydroxide will be having some acidic character. Compared to, I am not saying it is acidic, but as SROH whole 2 is more basic, so you can expect some acid-base type of reaction. Fine. So the logic is BOH whole 2 amphoteric, SROH whole 2 is basic, and the reason is down the group electropositive character increases, so basicity increases for the hydroxide compounds. Now this is the reaction actually happening. Here, these two hydroxide ion, if I am writing this molecule in this way, that is, I am separating it in cation and two negative anion HO minus. Same thing if I do for BOH whole 2 also, but I will not do so, because what is happening here, these two hydroxide, it is directly attached to this. Now BOH whole 2 is neutral molecule and you are adding two HO minus extra. So there will be some negative charge. So the anion that will be formed now, BeOH whole 4, there will be two negative charge extra, because we have added forcefully two hydroxide. So there will be two negative charge. And this negative charge will be neutralized by this Sr2 plus. So this is actually the salt form. Salt is overall neutral, but if you want to write its cation form, and that is if you want to separately write the cationic part and anionic part, then this is the cationic part, this is the anionic part. Okay. Now look at the statements. The first option is saying that Be is tetrahedrally coordinated in the ionic salt. Now surrounding Be, here we have total 4 HO minus. So this is true. It is tetrahedrally surrounded, 4 coordination number. The second option is saying that this is true. I am writing here T. Example of acid-base neutralization. This is also true. Both Sr and Be elements are present in the ionic salt. Now this is also true. Both are present in the salt, because from these two individual hydroxide we are getting a single molecule, which is the salt. So both are present. But the last statement is saying that the elements beryllium is present in the cationic part. But this is the cationic part where Sr2 plus is present. It is more electropositive. Be2 plus is present inside, but it is anionic part. So that is why this is actually the incorrect statement. So option 4 will be the correct option because we have to choose the incorrect option. Fine. Next question is related to carbonate. Now look at the 4 carbonates mentioned. The first one is carbonate of alkali metal, potassium. So it is a mixed question, both group 1, group 2, both elements are present. But all are carbonate. Then we have magnesium carbonate, calcium carbonate, BeCO3, beryllium carbonate. It is asking the following compounds have been arranged in order of their increasing thermal stabilities. Identify the correct order. Now, when we have discussed within a particular group, then we have seen what is the order of thermal stability for the carbonates. But here we have potassium also. Now, if you know the basic logic for when you are choosing the thermal stability order, it has some relationship with the size. Okay, and based on that, if you see in the first one we have K plus ion, then in the second one we have Mg2 plus, in the third one we have Ca2 plus, and the fourth one we have B2 plus. Now, if we simply consider only the group 2 elements, then the size is maximum for 3. Okay. After that, it is 2, and then it is 4, because this is calcium 2 plus obviously, and this is V2 plus. So this is the order of size, right? Now, if it is order of size, what about K plus? Now, K plus, as we know, when we compare group 1 and group 2, obviously the size is decreasing, right? Now, size is decreasing if we say so, and if we write that is period wise. So, if it is second period, third period, fourth period. So, in second period, group 2 we have beryllium, then here we have sodium, Mg, then fourth we have KCl. Now see, within a particular group, as you are moving down, size increasing, right? So K plus is very high compared to Na, and K plus is also greater than B, Mg and Ca. It is, first of all, if you compare with B and Mg, which is from group 2, period 2 and 3, so obviously K plus will be higher in size compared to B2 plus and Mg2 plus. Now, if you compare K and Ca, K plus will be higher because now you are moving from left hand side to right hand side in the periodic table, so size decreases. So maximum size that will be for potassium. Now, if we consider this logic, that increasing size of cation decreases its polarization power, polarization ability towards carbonate. So suppose I am writing the metal with some charge N plus, because two different types of charges are there. So in general, I am writing N plus, and it is associated with the carbonate ion. I am writing the carbonate ion in this way so that you can actually see the structure of it. Now, if the formula is K2CO3, then per carbonate 2 potassium plus. If it is group 2 elements, per carbonate there is 1 metal. But whatever it is, this will be the anode, and there is resonance also present. Now, when polarization power is maximum, what it will do? It will attract this negative charge, and as a result, this carbon-oxygen bond will be broken. And when this is broken, this metal will be now associated with oxygen, and CO2 will be removed from this part. That means when polarization power is very high, okay, then this CO2 removal, that will be very easy. So polarization power, it is inversely related to size. When size is very small, polarization power is very good, and when size is increasing, that is size of the cation is increasing, then polarization ability, that will be very low, and when polarization ability is low, thermal stability will be high. So polarization ability, that is also inversely related to the thermal stability. So considering all this, maximum thermal stability we will expect for potassium, that is K2CO3, because it is having maximum size of the cation. So 1 will be at first position. Now if 1 is at first position, the next position should be Ca2 plus. See, A and C you can easily cancel because at maximum position you do not have 1s. Only in option B and D we have first 1. But after that there is 3. So there is again tie. Next, if you move towards the third position, now there is 2 and 4. So the next will be for Mg. It is not 4 because Mg2 plus is larger than B2 plus. Okay. So this should be the correct option. So if I am writing it in terms of ion, K plus maximum, that is its corresponding carbonate, then Ca2 plus, Mg2 plus, and minimum stability will be for this one. So it is 4, this is 2, this is 3, and this is 1. So correct option is option B. So as we have finished all the problems related to salts of oxoacid of alkaline earth metals, the next topic is anomalous behavior of beryllium. So beryllium is the first element. Be, Mg, Ca, Sr, B. This is the first element, and first element of any group. It behaves differently compared to its other members. The same type of observation we have also seen for group 1 metals, that is alkali metals, where the first element is lithium, sodium, potassium. As we move down, lithium is the first member and its behavior is different. So there we have discussed anomalous behavior of lithium, but now it is group 2, so it will be anomalous behavior of beryllium. So here in this table we will see how what are the properties, both physical and chemical, where beryllium is behaving differently compared to the other members. It is harder, it is softer, higher melting point and boiling point, but for other members, that is if we simply consider the metal only, melting point and boiling point both are lower. Then here we have in the third point, reaction with water. Doesn't react with water even if you increase the temperature, but here for other members, reaction with water is possible. Now the explanation is, as we move down, there is increase in electropositive character, reactivity also increases. So that is why as we are moving down, there will be reaction with water. It forms covalent compounds, it forms ionic compounds. Now remember in the last slide, we have seen polarization power that is inversely related to size. So when size is very small, polarization power is maximum. Polarization power is maximum means covalent character is also very high according to Fezan's rule. So that is why Be2 plus forms covalent compounds because of its very high polarization power, but for other members that is not so high, so they form ionic compounds. The salts of beryllium easily hydrolyzed, not so easily hydrolyzed. Now hydrolysis capacity, that is also directly related to covalent character. As it is mentioned in the previous point, that it forms covalent compounds. Remember, when it forms covalent compounds are more prone to hydrolysis. So that is why if you know that it forms covalent compounds, obviously it will be more easily hydrolyzed compared to other members. Oxide and hydroxides are amphoteric. So based on this one problem we have solved. Remember the problem, the reaction between BeOH whole 2 and SROH whole 2. In today's class we have discussed. I'm talking about that one. So oxide and hydroxide of the first element, it is amphoteric in nature, but as we are moving down the group, there is more metallic nature generated. As a result, the oxides and hydroxides are basic in nature. The more anomalous behavior doesn't combine directly with hydrogen, doesn't combine directly with halogen, but direct reaction is possible for the other members, that is with H2 and halogen. So again, it is because of increasing reactivity down the group. Then the next one, beryllium carbide. that is BeC2. Beryllium carbide reacts with water to produce methane gas. So BeC2, when reacting with 4 molecules of water, there is formation of hydroxide. But what is the fate of the carbon in BeC2 molecule? The fate of the carbon is now it is forming methane gas. Okay. So here, if you are thinking about the formula, it is Be2 plus, because that is the only oxidation possible for beryllium. So C2 is basically carrying overall 2 negative charge. Okay. Carbides of other alkaline earth metals. Now see, the behavior is different. For BeC2, when it is reacting with water, there is hydroxide formation and methane. Here, in other cases, that is for other members, it is true we are getting hydroxide, but now we are getting acetylene gas. So behavior is different. Carbide of other alkaline earth metals, they are giving different byproduct. Hydroxide is fine, but byproduct is different. We are getting methane for beryllium carbide, but we are getting acetylene for the other members carbide. So C2 to negative, it is basically like this. Simply consider C111C. And first let me write acetylene. This is acetylene. Okay. Now if you are removing these 2 hydrogen, there will be 2 negative charge, right? There will be 2 negative charge, and that is actually C2 2 negative. But beryllium carbide, it is not forming acetylene. Now based on beryllium, its different compounds, we have this problem, and here among these 4 statements in blue color, more than one statement may be correct, because after all you have to choose the correct answer from the options given below. Option 1, 2 and 3, there is more than one statements, A, B, C, B, C, D, A, B. Only in last one it is a single statement. So it is statement or statements. Now one by one we will read the statements. The first one is saying that beryllium oxide purely acidic in nature. BeO. Remember in the anomalous behavior table we have seen that BeO, it is amphoteric in nature. It's oxide and hydroxide amphoteric in nature. And you cannot expect any acidic behavior from a metal oxide. And after all it is metal, alkaline earth metals. So you cannot expect any acidic nature. It is only possible if it is non-metallic oxide. For example, carbon dioxide. Then you can say it is acidic in nature. But purely acidic in nature, that you cannot say. It is actually amphoteric. It is not basic, but it is not acidic also. It is amphoteric. So this statement cannot be correct. So A is not correct. Next one is beryllium carbonate is kept in the atmosphere of CO2. Now this statement directly I have mentioned in the discussion of salts of oxoacid, for that is the carbonate salt. There this line is directly mentioned, and the reason is Lee-Chatelier principle. Fine. So BeCO3, if you decompose it, there is formation of BeO and CO2. And thermal stability is very low for this carbonate, because down the group thermal stability increases. So BeCO3, which is the first element's carbonate, its decomposition will occur very easily. So that is why the equilibrium, if you consider equilibrium, it will always be towards the left hand side, because there is a that decomposition is tendency is very high. So equilibrium mostly remain in the right hand side. BeCO3, it will always it is prone to decomposition, so it will produce BeO and CO2. But if you increase the concentration of CO2, that is if you keep the salt in atmosphere of CO2, now according to Lee-Chatelier principle, as the concentration of CO2 is very high, now the equilibrium will be shifting towards BeCO3. So when you want to keep BeCO3 in intact condition, that is you do not want the decomposition, but it is very prone to decomposition. Just to avoid that decomposition, you have to keep it in CO2 atmosphere, so that according to Lee-Chatelier principle, now the equilibrium will be shifted towards left. left hand side. So this statement is actually correct statement. Then beryllium sulfate, that is BeSO4. Down the group for sulfate, solubility decreases. That means it should be maximum soluble. So readily soluble, this is also correct. And last option, beryllium shows anomalous behavior. This is obviously correct because it is the first element. Now this question, see, even if you are having doubt related to B and C, because B and C comparatively, these two statements compared to A and D, it is comparatively difficult to remember. I'm not saying very difficult, but comparatively difficult, because it is very easy to remember that beryllium shows anomalous behavior. But if you are sure that this is true, that D is true, so in option 2 only there is D. So you can easily choose option 2. And one more thing is, if you are sure that beryllium oxide is amphoteric in nature and it cannot be acidic because it is not non-metallic oxide, so A cannot be correct. It is false. Now A is present in option 1, in option 3, in option 4. So all these are wrong. So based on this, any of these two, A, either A or D, then also you can choose that option 2 is the correct option. Fine. So there is anomalous behavior of beryllium as it is the first member, and we know that there is diagonal relationship also. Now diagonal relationship, if you consider for lithium, we have seen it. It has diagonal relationship with Mg. Just below lithium there is Na, and in the right hand side of lithium there is P. Now after that there is D block, then P block is started. Now in P block the first group is 13. Boron is first element, next element is aluminum. Now see, these two are having diagonal relationship just like between lithium and Mg. So here we will see what are the similarities present between Be and Al, that is aluminum. Now when we are saying that there is similarity between two elements properties, it has to, some things must be same, that is some information we will see, they must be same. For example, either their size or electronegativity or charge density, everything will be very close. That is, the values will be very close. Now, in case of these two elements, beryllium and aluminum, if you look at the size, radius of Be2 plus and radius of Al3 plus, they are not close to each other. So, size of these ions are not very close to each other. But if you consider charge density or charge by radius, same thing. Charge density means charge by total amount of charge, that is either 2 plus charge or 3 plus charge divided by the volume, or radius also you can take. So charge divided by R or charge divided by volume. Anyone you can take, because radius and volume, these two are related, directly proportional to each other. Now here if you consider that is ratio, then C by R value for beryllium 2 plus is 0.31 divided by 2 plus charge divided by 0.31. And the same thing if you do for aluminium, now it will be 3 positive charge divided by 0.5. Now these two ratio, if you calculate the values, you will see it is close to 6. That means this ratio is same for them. It is true their sizes are not very close to each other, but charge by radius ratio is very close to each other, and that is the reason why they are behaving similarly, because these chemical properties are directly related to charge by radius ratio. Another thing is their electronegativity values are, see, they are same, Pauling scale. So these are the reasons why we can observe some similarity in their behavior, beryllium and aluminium. So the similarities are, both these elements, aluminium and beryllium, they are rendered passive by nitric acid. If you treat it with nitric acid, what happens? On the surface, there is, suppose this is the metal, so on the surface there will be some coating of the nitrate salt. So, sorry, oxide, because This is oxidizing in nature. So there will be formation of beryllium, either beryllium oxide, if you consider Be element, or there will be aluminium oxide. The formulas are different obviously because in case of Be the charge is 2 plus, here it is 3 plus. So the oxide formulas will be different. But whatever it is, in presence of HNO3, there is formation of this impermeable layer of oxide. Impermeable means it cannot be, that is, this layer is so strong that other reagents cannot break this layer and further react with the metal. So in the surface region, there will be oxide of this, any of this oxide, depending on which element you have taken. But inside there will be metal present. But the outside reagent, they cannot reach the inside metal because of this impermeable layer of oxide. So it prevents further oxidation reaction. So that is why, though there is a tendency to react with nitric acid, but because of this impermeable layer formation, ultimately reaction will stop. Then the structure of beryllium chloride, if you consider, we have separately discussed it. The structure of BeCl2, and we have seen it in solid phase, in vapor phase, it is different. Solid phase, it is polymeric. Then vapor phase, it has dimeric type of structure. So if you consider that structure in vapor phase, then BeCl2, it forms this dimeric structure, just like AlCl3. In both cases, there is chlorine bridge. Okay. Both are soluble in organic solvents, that is, both these chlorides are soluble in organic solvents, and they behave as strong Lewis acid because of their electron deficient nature. Why they are electron deficient? Because if you simply consider one BeCl2 molecule, not the dimer, then see, here we have 2 electrons. So beryllium is using 2 of its electrons for 2 covalent bond formation with 2 chlorine atoms. Now surrounding beryllium, there is total 4 electrons. So it is not complete, is not fulfilled, so it is electron deficient. Same thing if you consider for aluminium, there is total 3 aluminium chlorine bond, and total number of electrons surrounding aluminium is 6. So octet is not complete, so that is why they are electron deficient and they are having some Lewis acid character. Lewis acid character means the acid molecules which are having tendency to capture lone pair or electron density from other species. So they behave as Lewis acid. And this is called Lewis acid catalyst, because in some organic reaction there is requirement of this type of Lewis acid catalyst. So this is their common application, and this is the structure for the dimer. Though BeCl2 forms polymer, but that is in solid phase. This is we are talking about for vapor phase only. So this is dimer with chloro bridges. Here also we have chloro bridges. Okay. Now details of this structure of AlCl3, if you are having any doubt, that it will be cleared in the corresponding group, and that is group 13. Aluminium is from group 13, and that is from P block, completely different chapter. Okay, we are not going into the details of AlCl3. Just remember here we have some similarities between this structure. In both cases, there is bridge of chlorine atom between 2 Be or 2 aluminium. Some more similarity. See, both these hydroxides, they are amphoteric in nature. Okay. Then beryllium carbide, aluminium carbide, both give methane gas. Remember in the table of anomalous behavior of beryllium, where we have seen the properties of beryllium which is not observed in for the other members. There you have seen this equation, that how beryllium carbonate, it is when it is treated with water, how we are getting methane gas, and there is formation of the hydroxide. Okay, the same type of behavior we also get in case of aluminium carbide. Okay, so in here also we are getting methane gas. So this is obviously a similarity between their properties. Then these two hydroxides, another similarity, when they dissolve in excess alkali. Excess alkali means suppose there you have provided excess hydroxide ion concentration, and that can be done by taking NaOH or KOH, which is the source of HO minus. So when these two are dissolved in excess alkali, then we get this type of berylate ion. This type of ion, remember when we have solved the problem, the reaction between BeOH whole 2 SrOH whole 2, then we have seen how it reacts with SrOH whole 2 and it forms this type of salt. Now in this salt, if you simply remove the Sr part, that is the cationic part, suppose I am removing it, rest of the part is BeOH whole 2 negative, which is basically this berylate ion. The same type of ion, that is excess alkali. In presence of excess alkali, it is also possible for aluminium. So here we have AlOH whole 4. Now the outside charge is single negative charge because aluminium is 3 plus. So 3 positive charge, 4 negative charge, 1 negative charge extra. But here it is 2 positive charge, 4 negative charge. So 2 negative charge extra outside the coordination sphere. But they are forming same type of ion in presence of excess hydroxide ion, or you can say excess in presence of excess alkali. Both these ions, that is Be2 plus or Al3 plus, I am writing it like this, have strong tendency to form complexes. Now when I am saying they have tendency to form complexes, that means see the complex example we have given with which anion? With anion F minus, that is fluoride anion. Now BeF4 2 negative, you can also put up third bracket here so that you can understand that this 2 positive charge is overall 2 negative charge extra. Be having positive charge 2 plus and with it 4 negative F minus. So 2 negative charge excess which is outside the bracket. But for aluminium, as it is having charge 3 plus and there is total 6 negative. So 3 negative charge will be extra. But they are, that is the way it is forming the complex, that with the fluoride and that behavior is same type of behavior. The oxides of both these elements, they are hard, high melting, insoluble, amphoteric solid. Hydroxides are amphoteric, oxides are also amphoteric. Here you can see they are amphoteric behavior. That means it can react both with acid and alkali. So BeO, it is reacting with acid. It is also reacting with hydroxide, that is sodium hydroxide base. So in presence of HCl, it is forming chloride salt. In presence of NaOH, it is forming Na2BeO2. So if I break it, it is basically 2 Na plus and BeO2, 2 negative charge, because par Be 2 positive charge and par oxide 2 negative. Now 2 oxide means total 4 negative. So that is why 2 negative charge outside, which is balanced by 2 sodium. So that is why the formula Na2BeO2 and water. Similarly, Al2O3, it can react with acid forming the corresponding chloride. It can also react with sodium hydroxide forming same type of salt. See, NaAlO2. Now AlO2 is carrying single negative charge. AlO2 carrying single negative charge. To balance it, we just need 1 sodium, because here it is 3 positive and 2 of oxide means total 4 negative charge. So the 1 negative charge extra balanced by sodium plus. So these equations are basically showing us their amphoteric nature. Now the next question is, what are the reasons for the anomalous behavior of beryllium? Why it is behaving similarly with aluminium, but it is not behaving similarly with the other members of its group? That is, I am talking about group 2. So the reason is, compared to other alkaline earth metals, in case of beryllium, it is very small in size because it is from second period, both atomic size as well as ionic size. Actually, the explanation that you are seeing here, it is also applicable for lithium. This is also because of small size, it is behaving different. So reasons are almost same. It is high electronegative. I will not say that it is non-metal. Don't think that I am trying to say it is non-metal, because when some element is having very high electronegativity, it is non-metal. For example, halogens, fluorine, oxygen. But high electronegativity, it is, we are saying it compared to the other members, because when you are moving down the group, metallic nature increases, electronegativity decreases. So if you compare it with other members, obviously it will have higher electronegativity. So you can also say that it is, rather than saying high, you can say higher. Then higher ionization enthalpy also, because down the group, because of increase in size, the removal of outermost electron, it doesn't require very much energy. But for the first element, the electron, the most loosely held electron that you are trying to remove, it is very close to the center nucleus. So it is not very easy to remove. So ionization energy is high comparatively. Polarization part is high. So we have seen it several times. And because of this high polarization of Be, it has some covalent nature and it forms completely different types of compounds. Okay. And absence of d orbital in its valence shell. Though it is obviously a difference with other metals, that is the next metal if you consider magnesium. It is true that in 3D there is no electron, but at least there is presence of 3D, even if it is vacant, but still there is some d orbital. But for beryllium, it is from second period, so no question of d orbital because there is no such 2D. It starts only from 3D. Okay. So absence of d orbital in its valence shell. Now the last reason, not much related, the whatever reactions we have seen for beryllium, where you have seen the difference with other members. The last reason is not so common, but in some cases, for example, you will see beryllium, it forms a 4 covalency compound. Coordination number maximum 4, not 4. It cannot exceed that. But for other members, it can exceed because of presence of d orbital. Okay. So only in some cases the last reason is applicable. But overall, all these are the reasons why it is behaving differently compared to its other members. Though we have been only 5 minutes, I will just give the introduction. Some important compounds of Mg and Ca. In case of group 1, remember, in group 1 we have seen some important compounds of sodium only. Sodium chloride, sodium hydroxide, all this. But when it is group 2, here basically we will focus on Mg. Now from Mg you can see only one compound we will discuss, which is its chloride. But look at the others, all are calcium. So for Mg it is only one compound we will discuss, but for Ca there will be 4 to 5 compounds, right? So the first compound for calcium is calcium oxide, CaO. It is also called quicklime. And always try to remember this, the other name that we use for each of these compound. Why it is so? Because in problems mostly this quicklime, the use of these terms, quicklime, slaked lime, limestone, they are very sound similar, very close term. There is some similarity, but don't be confused between them. Each is having different meaning. So when in the problem it is mention of quicklime, it is talking about calcium oxide. When it is saying slaked lime, it is basically calcium hydroxide. Then limestone, it is calcium carbonate. Okay. So the first one is oxide of calcium, hydroxide of calcium, carbonate of calcium. Plaster of Paris, it is sulfate of calcium, but it is not simply CaSO4. There is half water molecule of crystallization. And then there is cement. It is not that it is only, the composition is only made of calcium. There is also presence of some other species, other compounds. But calcium, its presence is, there is major presence. So these are the compounds we will discuss in the next class in detail. Okay. First there will be MgCl2, and after that, related to calcium, there is calcium oxide or quicklime, then hydroxide of calcium, which is also called slaked lime, calcium carbonate, also called limestone, then plaster of Paris with unique feature half H2O, because if you change the value half to some other value, it is no longer plaster of Paris. So don't think plaster of Paris is simply calcium sulfate, no. This is the unique composition. per CaSO4 there is half water molecule. Okay, then only it will be cluster of beds. So we'll end the session here. Thank you for listening.